Hello, and welcome to the fourth topic in the series that I'm recording related to artificial intelligence. And today we'll be talking about constraint satisfaction problems. And these are a class of problems which have been around for quite some time and are still historically relevant. And we always need to start off by coming up with a definition of what are these CSPs, right? Um, and they basically can oftentimes be expressed in as a class of problems known as map coloring problems. The idea is that you have n variables. In this case, there are x1, x2, and so on. You've got D domain, so that's the domain in which those variables exist. There's some constraints, states, and then a goal test, and then successor function is the basic idea. So what we're and you're done whenever you satisfy all the constraints and have completed the process. So what is it for? And this is basically around doing things like in a single agent deterministic set of actions, you have full observed world, right? So you can see all of the world and so on. So that's what the search is for, is finding things inside of that domain where you know basically everything. You're able to see all of the board, if you will. You make some assumptions about the world, that is, that you see it all. Then you move into the planning stage of things, and you come up with a sequence of actions. That's what a plan is, a sequence of actions with the intent of reaching some goal. Different paths have different costs and depths and associated with them, potentially various factors, time, and so on. And so you'll want to oftentimes minimize the cost, be it time or whatever it might be. Heuristics are one way of doing this. They give some problem-specific guidance. So depending upon the problem, you come up with a set of rules that are used in your heuristics, so very simplistic rules of thumb, if you will, or rules that you apply very loosely. And so the idea here is that the assignment of to variables is what's important, not necessarily the path to get there. So and so for some formulations, you may have all paths at the same depth, otherwise you may not. And it's basically a form of an identification problem. And it's used for identifying things, in particular coloring graphs such that no two things that are touching have the same color is the basic sort of kind of guideline. So it's a standard set of search problems. Your state is a black box, meaning you don't know it necessarily, but it is, things are stateful. The goal can be some function over a set of states. And a successor function can be essentially anything. It's how you know when you're done, right? And so the CSP is, to say it more formally, it's a special subset of search problems. So it's a kind of search involving state, where state is defined as all of the variables x of I, with values from a given domain. So a particular domain, capital D. And sometimes D depends upon I. And the goal test is a set of constraints specifying allowable combinations of values of subset of variables. So the basic idea here is that you're trying to color all of a map in such a way that it is maybe uses the least number of colors or something, and a certain amount of maybe time or whatever the rules might be. So an example here, you have a map of Australia with the various territories inside of it, or states. And so for simplicity, we abbreviate Western Australia as WA and NT is territory and so on. The domain is, in this case, the three colors that we have access to. And adjacent recent regions must have different colors. That's our one constraint. So WA can't be the same color as NT, nor can either of those two be the same as South Australia, so S2. And so explicit is that WA and NT are made up of the colors, and you come up with the enumeration of the possible colors. And so solutions are assignments that are satisfying those constraints. So a solution is any set of colorings upon those domains, those nodes in this graph, essentially, that don't break the rule, right? So no colors have the same, no adjacent items have the same color. And so a solution is presented on the screen there. You can see that there's no two things touching that have the same color. And they're all colored with a color. So you may also view this as a graph where there is no connection between Tasmania and the rest of Australia because it's on an island. Yeah, so we can look at it as those items that have colorings must have a line between them, and those that don't have no line. Another example of a different set of problems is the N queens. So the formulation is basically around where all can you put your queens on the board such that they don't kill each other automatically, right? Or how many can you put on the board so that you can they not be in competition with each other. And in particular, you would formulate this problem as the variables are each of the open squares. The domain is from 1 to 9, and then the constraints, and this is essentially, it looks like Sudoku is what we're doing, not counting nines or queens. Oh, sorry, we moved on to Sudoku. So this is basically a similar sort of challenge. You've got the domains of the subgrids, you've got the columns and the rows, and you basically have the rules that you can only have a number in a column, a row, or inside of a domain once, right? So that's the basic idea. And given that problem, you formulated this in a way that could potentially be solved using various approaches. We do these in lots of real world scenarios. This isn't just something that's hypothetical. Examples being who teaches on what dates for assignments if you're in the teaching world, a timetable of what class is offered when and where, be it the time of the day or the part of the year. If you're talking about hardware configuration, transportation scheduling, factory scheduling, circuit layout, all kinds of things are bounded by this sort of challenge. So it's a very real world problem that has been using AI techniques for years. So moving on, again, solving with complex or with CSP, so these constraint solution problems. So you basically idea is to combine together with this inference. So the idea of inferring a solution, and inference was very prevalent in expert systems. The idea of a inference in an expert system was given fact A and fact B, figure out some new fact that relies upon those two facts, and it was quite good at that. There's also various other types of inference inside of AI, but it's basically that concept, taking two things that are known and coming up with a new thing that maybe was unknown beforehand. So that's where, when we're dealing with a search inside of CSP, we may use inference as a way of also searching. You may also do some form of like filtering, of removing those that aren't the answer. So kind of akin to pruning. And so basically, if you come across some bad options, remove them from future considerations. So ones that you know will never allow a successful solution elsewhere, by removing those, then we can not have to look for as many options. So whenever you're marking off all the ones that are not going to do well, we can start enumerating some of the possible poor choices, and you're reducing your search space then. So that's the basic idea, is to apply similar concepts as we have for other problems, such as expert systems and so on, to this particular domain, and reuse those concepts in this world. And that's one of the key things with AI in general, is that we may leverage concepts in from that discipline in all kinds of places. And in fact, if I look back over my career over the past 30 plus years, I've been using those concepts I learned as part of my undergraduate and graduate that related to artificial intelligence throughout my career, even though some of the projects may not look like it on the surface. It is something that is the reuse of these concepts and approaches are very prevalent. So the basic idea here is that we are looking at forms of consistency across and dealing with these approaches. So some of the approaches may be reminiscent of other approaches, such as various other types of searching and so on. There are oftentimes that similarity. We also have ideas of arc consistency, so making sure that a way of making sure that the graph is kept to be consistent or in a valid state as we're going through it. The idea here is that you can have one solution left or maybe multiple solutions left after you've removed the various arcs. Backtracking search for CSP. Backtracking search is a form of search where you can go to a point, and as the name implies, you kind of roll back a little bit and then go forward again. So you're going down, maybe you're doing something that's similar to depth first, and that's kind of what we're looking at here. And it's essentially an improved depth first search. You start off at a particular location. You start going down. Whenever you run into one that isn't valid, you're going to go essentially a form of a backtrack. You're going to go back up and try it again. There's also concepts of localized searching as well. Whenever you're dealing with complex problems, sometimes we break those problems down into more manageable problems and we apply it to that particular subset. So an idea here of using various approaches across. Here we're moving into iterative algorithms for CSP. A similar sort of challenge, so that you're basically using concepts from other forms of searching to apply in this space as well, and trying to avoid or to locate the minimum or the maximum. So if you're dealing with hard problems, that may be something that we take into consideration, is applying different sets of skills. When we deal with difficult problems, one of the key things that we want to do is make sure we take a look at how we're structuring that problem. So we've already talked about in this case that you may have the extreme case of independent subproblems, so that each subproblem can be solved independently and the combination merged together. For in this case, the example is Tasmania versus the rest of Australia. Those can be solved independently. But that's probably not going to be as common as those that have some sort of subcomponents that maybe could be solved, but not necessarily all in isolation. So taking the bottom example, suppose that you have a graph of n variables that can be broken into subproblems of only C variables. So your worst case solution is big O of N over C times D to the C. So generally speaking, it's potentially doable, but it is going to take a while, right? So when we start dealing with such things, we may be looking for other ways of breaking them down. And in this case, we're looking at tree structured CSPs. So there's no loops. Trees are special constructs. There's no loops. There's sometimes a direction. In this particular case, there's no direction. And later on, we'll be talking about things like probabilistic reasoning. So essentially using a certain confidence or probability of correctness with a particular choice. In this case, we're not there yet. So the way that you'll address these is somebody gets to be the tree. So you're going to pick one of the nodes and pick it up and hang it up from it, so to speak. So in this case, we're going to say A is the root, and we hang everything off of it and look at it from that perspective. Also introducing directionality. So we've now switched from an unordered graph to or undirectional graph to a graph with direction that is also a tree, a very special sort of thing. And given that, then we can start applying some sort of tree-based approaches and remove inconsistent nodes along the way and come up with a solution. Um, so with that, we can also improve that structure over time. So with the idea of basically conditional of a pruning of a particular neighborhood, graphs have this concept of a neighborhood, which is important to understand some of this terminology. So it's similar to what you would think. It's nodes that are close to each other in some fashion. So you could argue that maybe ones that are one arc away would be considered a neighborhood. Neighborhoods can overlap, but they can also be oftentimes segregated depending upon the type of graph. So and with this, I'm going to go ahead through some of this because this gets into a lot of depth that, frankly, you may not care about too much at this time. Tree decomposition, similar concept to some things that you may have seen elsewhere. You take it and turn it into simpler trees and basically decompose it into something that's easier to be addressed. So with that, we've talked a good bit about CSPs. Special kind of search problem. States are part of the are partially assignments or assigned. The goal test is defined by the constraints. So did you succeed or not determines by the constraints being satisfied. There's basic approaches, backtracking searches. There's ways of speeding it up, such as ordering, filtering, or structuring it. And those are all things that we just went over very quickly. There are also some ways of doing things in an iterative fashion. You may also be doing things like doing things in a more recursive sort of approach versus iterative or ordering iterative, but they're very similar. Ordering the minimum remaining value. The basic idea here is that we've got a minimum remaining value, MRV. We choose the variable with the fewest legal left values in its domain. So pick the thing that is essentially the hardest to color with the fewest legal left values. So you pick, this is a very heuristic driven search, right? So you're picking the one that that has the fewest legal values that are left and use it to satisfy the currently selected item. Why would you do the min rather than the max? It's the most constrained variable is the reason, right? So we're looking for the one that you're going to run out of places to put it the quickest, right? And that's kind of this fail fast kind of concept. And so you're essentially ordering so that you're ordering them in such a way that you get the ones that have the least choices. So you may want to work with a rubber duck sometime whenever you're writing things down. That's the paired programming concept where you use a rubber duck as your co-partner. If you have any questions about this material, let me know. Hope you enjoyed it. Like and subscribe if so. If you have feedback, feel free to share. Stay safe. I'll talk with you soon.